Hello, everybody. Let's start. So I first want to clarify something that I said last lecture concerning faces. So I said I sort of tried to define properly, or as best as I could, top of my head, a face, and what I said wasn't quite correct. Not a huge deal, but let's fix this. So let's see. So comment about faces. Okay, so let me remind you of the situation. I have a graph G, which is, let's say, planar. So it has a planar representation, and what does that mean is that we have points in the plane which represent the vertices of the graph, and we have curves which connect vertices which are adjacent. And the key point is that these curves do not intersect. Okay, so they might meet at these points which represent vertices, but nothing else. Okay, and I vaguely defined a face as a cycle in the graph where the region inside does not contain any points from the representation, but that is not quite correct. So let me show you the obvious problem with this is if I have something like this, for instance, right? So clearly this face does in fact contain, but what we understand intuitively by a face, it contains points which are vertices of the graph, right? So so we have to modify this slightly, and I tried to find a very simple way to write down a definition, and I couldn't. I mean, it's possible. Basically, what you want is to look at the induced subgraph corresponding to all the points inside the cycle, and you have to add some sort of condition on the connectivity when you remove two edges. I mean, it's a mess. So we'll keep it intuitive. Okay, so intuitively, okay, I'm afraid it has to stay that way. A face is a region bounded by a cycle in G such that the region, I'll say inside, contains only trees. And I won't go, okay, so what is disallowed is having paths that will either a cycle inside the face so that it wouldn't be, I mean, you can't allow that, but you can't even have a path connecting two vertices inside the face, right? So for example, the following are forbidden. So if I look at this cycle, if I have something like this, then this outside cycle is clearly not a face. This is not a face, right? The outside one. And another possibility would be something like this, where we don't have a cycle inside, but we might have, let's say, a path like that. Then that obviously the big cycle is not a face, right? So this is not a face either. There are two faces there, okay? So the only possibility of having vertices inside is these little trees that are glued to to the vertices on the cycle. Okay, but I don't want to go further than that. I think everybody understands intuitively what I'm talking about, and I don't want to go further than that. So now I'll need the following concept for today, and once because I have my hands in this, let me tell you what I mean by that, and after that I'll tell you what I'm going to talk about during this lecture. So so we'll say, let's not do it in red. So note, we will say an edge bounds a face if, and again, I don't want to go to try to be totally 100% precise here because it gets really heavy, but it is exactly what you think it means, is either it is an edge on the bounding cycle that defines the face, or it is one of these edges that are little trees that are hanging around, right? Or it is entirely inside the face. So for example, like these, right? Okay. And again, it's also a possibility that as a planar graph, you have just a tree, so you have no bounding edges of any kind except things like that, right? So that's another possibility. Okay. So that's what I wanted to say about edges and faces. The only obvious thing here, I think this is obvious, is that if you have an edge, it bounds at most two faces, right? So notice the obvious fact, an edge bounds at most two faces. I will use that in just a sec, okay? But I think this is clear, right? So either there's one face on either side or it's inside one face. So, okay, so what are we going to do today? So last time we saw Euler's formula, and I'd like to use it to prove two small, very shortly proved results that we will use later in two different contexts. One is the 5-color theorem, and the other is when we classify Platonic solids. And these are useful tools to prove that certain graphs are not planar without getting your hands dirty. Okay, so two results that follow from Euler's formula. Okay, and I will talk about Kuratowski's theorem. I will state it briefly. I will not prove it because it's actually pretty tough. But I will state it because it's easy to state and it's a beautiful result about planar graphs. It tells you exactly how to recognize planar graphs. Okay, so let's go to our two results. So again, Euler's formula, let's restate it. I have a graph G, which is connected, planar, and it's a simple graph. I'm considering only simple graphs here. And as I said, you can always, if you wish, extend these to graphs with loops. It's very easy. And you can extend these to multi-graphs. Again, this is fairly easy too. There are no real difficulties to go further, but let's just keep it simple. Haha. So what is Euler's formula? It says that if you count the number of vertices in this graph and you subtract the number of edges and you add the number of faces in some planar representation, you will always get 2. Okay, so this is Euler's formula, which we proved last time. I found a nice little video, which you may have found. I know it's 7 minutes long. I looked at it and I was really excited the first 4 minutes because it gives you a different proof of Euler's formula. But although I mean, it's snazzy looking, it's really just like beautiful animation, and the gentleman has a lovely voice. But it sort of fools you into thinking that what you saw is a very simple proof, but there's actually a lot of stuff that's hidden and just shoved under the carpet. But it is nice. I mean, if you see it, I can send you the link if you're interested. Just let me know. I might put. I'm not sure. I almost sent you a message yesterday with the link, and then I looked at the end of the video and I said, nah, I wasn't sure. But well, okay. So here's our first result, which follows from Euler's formula. So here is, so let G be a connected planar graph. And again, I'm not writing that it's a simple graph. I'm assuming all graphs are simple here. Okay. With E edges, V vertices, and I will assume that it has at least 3 vertices. Then E is less or equal to 3V minus 6. I mean, that looks a bit silly, right? E is less or equal to 3V minus 6. But notice the difference with Euler's formula. Euler's formula involves the vertices, the edges, and the faces, right? So to talk about faces, of if I just show you a graph, you can't talk about faces because it's not a planar representation. You need a planar representation to talk about faces. This corollary, in fact, does not talk about faces at all. This is an inequality that you can verify for any graph, right? And if it doesn't hold, then you know your graph cannot be planar, okay? So we'd like to prove this. So it's a necessary condition. So this is a necessary condition for a graph to be planar. Connected graph. Okay, so if this condition fails in a graph, and you can check this just if as long as you, I mean, if I tell you what the graph is, you know the number of vertices, you know the number of edges, you can check if this inequality fails, then you know your graph is not planar. End of story, right? You don't have to mess around with pictures or anything. That's it, right? It's just an inequality, arithmetic inequality. Okay, so how do we prove this? This is actually pretty straightforward, very standard kind of argument. So the trick is this. So we are going to look at faces. I mean, I have to use the fact that this is a planar graph, and Euler's formula by itself is not going to be sufficient. So this is Euler's formula there. So I need to just do a little analysis of bounding edges of faces. Okay. So first fact. So fact 1. Every face is bounded. Remember what I said, how I define an edge bounding a face is that it's either the cycle around that face or those edges in trees which live entirely inside the face. Okay, so I'm claiming that every face is bounded by at least 3 edges. And if you think about this just a few seconds, like a budding mathematician, you will raise your hand and say, wait, that's not true. That's false. So yeah, it is false. So why did I say that it's a fact? So help, what's going on? This is false. But it's false for only one graph. And that graph is this one. Notice, I mean, recall that we're making the assumption that our graph is connected, it is planar, and it has at least 3 vertices. But this guy, this graph here, the path of length 2, you have only one face, which is the unbounded face, and it's bounded by only 2 edges. That's bad, right? However, but the inequality is true for this graph, so I can just forget about this guy, but E less or equal to 3v minus 6 is true here. Right? There are 2 edges, and 3v minus 6 is 9. Minus 6 is 3, right? So it's true here. So we're going to forget about this only counterexample to our fact, and any other graph, this will be true, because either you have a bounded face and then the cycle has to have at least, right? So we forget, let's just write, okay, sorry. So we forget about this graph. It's done. Okay. Okay. So in any other case, either a, so in all other cases, if the face is unbounded, then there are at least 3 edges that will bound it. You can see that if that example is the only one with 2 edges, there exist at least 3 edges bounding it. And if the face is bounded, if it's inside a cycle, the cycle itself must have at least 3. So if face is bounded, bounding cycle has at least 3 edges. Okay. All right. If the unbounded thing annoys you, just put the whole thing on a sphere. Okay. So if there is no bounded, so either on a sphere, either every face has a bounding cycle, or otherwise it looks like that little graph is just a little tree like that. But I've disallowed the smallest case, which has only 2 edges. Any other case will have at least 3 edges, so we're fine. Okay. So every face is bounded by at least 3 edges. Okay, so here's my first inequality. So given any face, big F, I'll call degree of F will be the number of edges that bound it. Okay, and by the way, what I've just done is the hardest part of the proof. The rest is really super easy. Okay, so given any face F, let's call degree of F the number of edges that bound it. So what I've just proved is that this number is at least 3 for any face. So if I add up all these degrees, I get something which is at least 3F, little f being the number of faces. So by the above, I get that 3F is less or equal to the sum of all degrees. Right? So if I take all the faces, I add the number of edges bounding each face, which is at least 3. So it'll be 3 times the number of faces total, right? So little f is the number of faces. Okay. So that's our first inequality. That's our first fact. Fact 2, right? And this is what I've said earlier. Each edge bounds at most 2 faces, right? So each edge bounds at most 2 faces. Okay, so that means that if I add up all these degrees, I will get at most twice the number of edges, since each edge bounds at most 2 faces. When I'm counting, I take a face and I'm counting all these edges on this face. Each edge will be counted at most twice because it can be in at most 2 faces. Okay, so now I combine these 2 facts. I get that 3 little f is less or equal to 2e. Okay, and we also have Euler's formula, right? V minus e plus f is equal to 2. Okay, so I would like to combine these 2 things. So what I'm going to do is I'm going to multiply Euler's formula by 3. So I get that 6 is equal to 3v minus 3e plus 3f, Euler. And this here tells me that 3f is at most 2e. So this, I'm going to replace this. So 3v minus 3e plus 2e by star, right? I've replaced the 3f by 2e, so I get something bigger. So I've got that 6 is less or equal to 3v minus 3e plus 2e, and basically we're done, okay? So 6 less or equal to 3v minus e. So e is less or equal to 3v minus 6. Okay? So that's it. Okay, so basically the trick is this: just count the number of edges that bound each face. You get these 2 inequalities, one which is, well, each face is bounded by at least 3 edges, and the other one is each edge bounds at most 2 faces, and from this you get that E is less or equal to 3v minus 6. Okay, let's just apply this immediately to the graph K5. And you'll see how easy this is if you're lucky, right? So K5, what is that? The complete graph on 5 vertices. So this. This is K5. It has 5 vertices. And as you could see, the way I drew it has 10 edges, right? So let's see, 3v minus e, this is 15 minus 10. Is that right? Yeah, what am I doing? Sorry, I want 3v minus 6. Sorry. 3v minus 6 is 15 minus 6, which is 9. Right? And E is 10. So 10 is not less or equal to, so E is not less or equal to 3v minus 6. This is 10, and this is 9. Okay, so the complete graph on 5 vertices fails this inequality, and so it cannot be planar. And that's the proof. I mean, that's as easy as it is, right? So unfortunately, this will not work for all graphs, right? So there are graphs which, for example, K33 does not fail this inequality. That'd be really too cool. It doesn't work. In the book, there is a slight variant of what I just did to get an inequality that K33 will fail. I'm not going to do it here, okay? Because I won't need it later. And there's just so much I can do. Okay, so this first result shows us that K5 cannot be planar. Here's our second corollary, which is even easier to state. And it's a fundamental observation, which is this. So every connected planar graph has a vertex of degree at most 5. So recall what the degree of a vertex is. That's the number of edges incident to this vertex. Okay, so if you have a graph and you see that every vertex has degree 6 or more, that's it. It can't be planar. It's not possible. Okay, so let's try to prove this. Okay, so I would like to use the previous result. Okay, and the previous result, be careful, you need at least three vertices. So let's get rid of the case where there's less than 3 vertices, and then this is obvious, right? So if G has at most 2 vertices, the result is obvious, right? I mean, yes, okay. So assume G has at least 3 vertices. Okay, last result says that E is less or equal to 3V minus 6. Okay, so we know this. Let's assume for a contradiction, okay, that every vertex has a degree at least 6. Okay, so assume for a contradiction that the degree of X is greater or equal to 6 for every vertex. I shouldn't write this because I never use this notation. Let's okay, so suppose for a contradiction that every vertex of our graph has degree at least 6. I'd like to combine these two things together. You might remember the handshaking lemma. The handshaking lemma says if you count the number of handshakes that everybody gives at a party, you'll be counting twice the total number of handshakes, right? In other words, 2E is equal to the sum of all degrees, right? So if you count all the edges incident to every vertex, you'll be counting every edge exactly twice because you'll count it for one side and then you'll count it for the other, right? So the handshaking lemma says that twice the number of edges is exactly the sum of all degrees. Okay. Now, if every vertex has degree at least 6, if I add up all these degrees, it's 6 each time, at least 6 each time. So this thing will be at least 6 times the number of vertices, right? Okay. So now I've got that 2E is greater or equal to 6V. but also I've got that E is less or equal to 3V minus 6, and these will clash, okay? Okay, but this will give you, if E is less or equal to 3V minus 6, multiply everything by 2, you'll get 2E less or equal to 6V minus 12, which contradicts 2E greater or equal to 6V. So that's the proof. Okay, so any planar graph must have a vertex of degree at most 5. There has to be one in there. And this we will use in a crucial way when we prove the 5-color theorem. What's the 5-color theorem? I've mentioned it a couple of times. You remember I talked about this puzzle that somebody asked a long time ago in 19th century. If I have a map of countries and I put different colors for countries that share a border so that I can read the map better, can I always color these things with at most 4 colors? And so that was a problem that was open for, I think, over 100 years, which essentially translates to, does every planar graph have a proper 4 coloring? If you remember what a coloring is you give colors to the vertices, and if 2 vertices are adjacent, they must get different colors. Okay, so it turns out this is true, that every planar graph is 4 colorable, but this is very difficult to prove. A long time ago, 100 years ago, it was proved that something a bit weaker, so 5 colors suffice, and I'm going to show you the proof because it is very nice. And this is one of the ingredients in the proof. Okay, so let's move here. So we've seen two examples of non-planar graphs. K33 is not planar. And we've seen that K5 is not planar. So obviously we can create tons of non-planar graphs just by taking graphs with vertices with high degrees, right, everywhere, just by the last result. But it turns out that in a certain way, these two guys are the key non-planar graphs. And this is the contents of Kuratowski's theorem, which is really remarkable. So let's start by, I'm going to show you a little baby construction, which is like a very, very, very stupid construction, very easy to understand, and to see its connection to planar graphs, okay? And then we'll see that this construction plus those 2 graphs, you've got everything you need to understand planar graphs and non-planar graphs in a certain sense. Okay, so here's a definition. So this is something I want you to keep in mind, okay? And now something which is not really related. So let's say I take a graph G. Okay, and I want to construct a new graph from G in a very, very simple way. So here's the way I'm going to do it. I'm going to take an edge of G, and I'm going to basically add a vertex in the middle of the edge. Okay, I'm going to subdivide this edge. Okay, so I want to write this properly. So the graph H is obtained from G by an elementary subdivision if, so what does it mean? If there exists, so there is an edge, let's call it E, connecting vertices U and V in G, such that H is obtained from G as follows. So first, you remove the edge E. Okay, so you take the graph G, you erase the edge between U and V. Okay, and then what you do is you add a new vertex, W, and edges U to W and W to V. This is all undirected graphs, right? Okay, so here's the situation. You have G like that, and inside G somewhere there's, I'm not talking about planar graphs or anything here, it's just any graph. Okay, so I have an edge UV like that. What is H? It is exactly, let's be fancy and use the technology. Like that. So H, it's the same thing as G, except that you subdivide the edge. So by you have a new vertex W and edges U, W, W, V. Notice that there is no edge between U and V. This is gone. Okay. So this is what we say when we say H is obtained from G by an elementary subdivision. Okay. So here's a bunch of graphs that I can obtain by subdivisions. Let's say I start with this, and then I can subdivide the edges. So now I can get this. So you can see that all the cycles, by successively subdividing, I can subdivide all the edges to get bigger cycles like that. I could, let's say I have K5 like that. I could subdivide I can add a vertex here, for example, right? And I could, no, like this, maybe like that, maybe another one like that. And I could keep on going by subdividing like this. But what I want you to observe, hopefully you see this, is that if you start with something planar and you do an elementary subdivision, you still get something planar. And on the other hand, if you obtain something that is planar, it's because you had something that was already planar, right? So this is the observation I want to make, which is obvious, I think, right? So if H is obtained from G by elementary subdivision, then H planar if and only if G planar, right? So if I start with something planar, I'm going to get something planar. If I get something planar, it's because I started with something planar, right? Okay, so that's the first observation I wanted to make. The second observation, and I mean, this is like even obviouser. If K is a subgraph of G and G is planar, then, oh man. Then K is planar. So I mentioned that last time, right? If you remove stuff from a planar graph, you're not going to create something non-planar, because you're not going to create, if you start with a planar representation, if you remove stuff, you're not going to create any crossings. So nothing wrong can happen, right? So let's put all of this together. Let's go back to what I said here. I said that K33 and K5 are not planar, right? Which means that anything obtained by subdivisions from these guys cannot be planar, right? And so it means that so all of this together, all of the above together, a planar graph cannot contain a subgraph which is obtained from K33 or K5 by a series of elementary subdivisions. I really want to say that. So by a sequence of, okay? So if you take K33 or you take K5 and you start subdividing, you're always going to get non-planar graphs. So if that graph you get is a subgraph of a bigger graph, then that bigger graph cannot be planar. Okay? So up to this point, we haven't done anything deep. This is just like, I mean, we use the fact that K33 and K5 are not planar, which we had to work for, but otherwise, this is just a very, very silly observation. What is not an obvious observation is that, in fact, that's it. That's the end of the story. So this is Kuratowski's theorem, which is a remarkable theorem. Did I write what year this is? This is early 20th century. I didn't write the year. That's silly. It's certainly in the book. Kuratowski's theorem states that a graph is planar precisely when it does not contain a subgraph which is obtained by subdivision from K33 or K5. So this is really, and let me state it in the negative way. So G is not planar if and only if G has a subgraph obtained from K33 or K5 by a series of elementary subdivisions. This is not obvious. It's not obvious at all why this should be true. I don't think there is any, I mean, it doesn't use like, it's a very combinatorial proof, not very exciting proof, but this is not obvious, okay? So basically what it says, if you take a graph which is not planar, the reason why it's not planar is because inside somewhere there is essentially K33 or K5 hidden in there with subdivisions, okay? To illustrate this, I'm going to do an actual example to illustrate this. Now, notice that this is not, as stated, this is not algorithmically very, very sound in the sense that if you start looking for subgraphs, if the graph is way big, I mean, this is not good, right? You're looking at way too many cases to check. It's totally exponential. I mean, the number of subgraphs is clearly exponential in the size of the graph, right? This number of subsets is 2 power n, right? So this is no good. But aside, recognizing planar graphs is a algorithmically easy thing, but it doesn't use that. right? Or at least not in this, not stated this way. Let me show you an example. So here is a very famous graph, Peterson's graph. It's famous because, well, all sorts of reasons. One of the reasons is rule of thumb. If you're trying to, if somebody asks you, conjecture, is this true for all graphs? Usually trying Peterson's graph first is good because it might be your counterexample. Somehow it's often a counterexample to quick conjectures, right? Or quick counterexample to conjectures. Here it is. Here is Peterson's graph. So you start with a 5 cycle. It's a very good looking graph. You start with a 5 cycle, and then you add 5 vertices like this, one adjacent to each of the vertices in the 5 cycle. And then you have another 5 cycle, but you skip a vertex each time. So you go this way. This is Peterson's graph. Okay. Now, question, is it planar or not? Clearly, this is not a planar representation. There are crossings everywhere, but maybe there is a way of doing this. Okay. If I'm asked to check if a graph is planar or not, the first thing I'll check probably is, well, let's see, is there a vertex of degree at most 5? Yeah, there are tons. They're all at most 5. So that's not going to work. Maybe E is not less than 3v minus 6. Okay, let's call this G. Okay, so I'd like to check, because if that fails, I'm done, right? So what is the number of edges here? E, so 5, 10, 15. And there are 10 vertices. So 3v minus 6 is 30 minus 6, which is 24. So 15 is less or equal to 24, so true. Okay, so I didn't learn anything from this inequality. Okay, so it doesn't tell me anything. Okay, but I'm going to show you that G is not planar using Kuratowski's theorem. Okay, but G is not planar using Kuratowski's theorem. Okay, so here it is. So again, if you're looking, you have to mess around with this, and I'm fortunate enough to have the solution in my notes here, so I don't have to mess around live here. So here we go. So I'm going to copy this. Maybe I'll be lucky and I can use technology to my advantage. Okay, so the vertices I'm interested in are the following. Let's put them in blue. So this, 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 and this. Okay, so basically these are the vertices I'll be interested in. And so again, I'm looking for a subgraph, which is a subdivision of K5 or K33. Okay. Okay, think about this. It's easy to see that what you're looking for is not going to be K5. There's a simple reason why what we're looking for is a subdivision of K33. If you stare at this graph a few seconds and think about it, you can figure it out. I won't tell you now, but okay. So now what I'm going to do is I'm going to erase this vertex here, and all the edges which are incident to it. Okay, so I'm looking at this subgraph. Okay, so this is the subgraph I'm interested in. Now notice that I can view certain things here as subdivisions, right? So look at those two top blue vertices, right? So there's an edge going up to the top vertex and then going back down to the other blue vertex. That's a subdivision, okay? So, okay, let's, I'm just gonna copy this, put it over here. Okay, so you see that, right? So this is okay. Let's redraw. Okay, I know what I want to do. I'm gonna do this. Okay, this is the same as this, right? And these two, like that, and these two. So I'm just redrawing my graph so that you can see better that these are subdivisions. Okay, so same. Okay. And now, so let's now forget about the, so this subgraph of G is obtained by subdivision from the following graph. So this is same as this, which is obtained by, by 3 elementary subdivisions from the following. Okay, so that was my subdivision of this edge. This is the subdivision of this edge, and this is the subdivision of this edge. Okay, so again, I started with the Peterson graph. I forgot about one vertex and the edges incident to it. Right. Once you forget a vertex, you can't talk about edges incident to that vertex, obviously. And so now I have the subgraph of G, which is obtained by subdivision of this last graph that I put here. So what is this graph? Let's see. Let's give names to these vertices. Let's call this 0. Let's call this A, B, C, 1, 2. Okay, so I'm just going to redraw it. 0, 1, 2, A, B, C. I hope this is right. So 0 is adjacent to ABC. 1 is adjacent to ABC. And 2 is adjacent to ABC. Yeah. This is K33. Okay. So that's it. So that's a proof. I don't need Kuratowski's theorem, right? I just, it inspired me to look for that because I know I must find it, but I'm not applying Kuratowski's theorem in the sense that I don't need its full proof. I've just proved independently of Kuratowski's theorem that the Peterson graph is not planar because I found a subgraph, which is a subdivision of K33. Now, if my graph were planar, this would have to be planar also, which we know it is not. Okay, so G is not planar. Okay. So hopefully you see how this works. So to recap, I've used Euler's formula to prove two little facts about planar graphs, which are that E is less or equal to 3v minus 6 if we have at least 3 vertices, and that there's always a vertex of degree at most 5. And I've presented Kuratowski's theorem, which characterizes planar graphs or non-planar graphs, depending on your point of view, via elementary subdivisions and the two basic non-planar graphs, which are K33 and K5. I think in the book they state this theorem in a slightly different way, which is more complicated, and this is correct. This is the same thing. Okay, so I'll if you have questions, just send them to me, and otherwise I'll see you next time. Cheers.